Okay, well, I'll say just a few words then to kick it off for anyone out there that, that doesn't know me or is new to the LJC, or for those watching afterwards. So it's a bit of background and a bit of a call for help. So my name is Barry Cranford. I'm the founder of the London Java community. I'm not a developer myself. I run a tech recruitment company called RecWorks. So here at RecWorks, we've been on a mission for about the last 12 years to prove that recruitment can be a force for good in the tech industry, beyond just getting people jobs. And that's specifically around learning, mentoring, career development, and that kind of thing. Put simply, if people want to learn and other people are happy to share, then we're happy to draw the lines between that and put on events like this. So that can be on a group basis like today, and through communities like the LJC, or it can be on a one-to-one level. So the biggest example of what we've got is the Meet a Mentor community, which has got really close links to the LJC. And within that, we organize introductions between mentors and mentees at all levels. And this is what we could really do with some help with. So we've always got a need for new mentors. There's always new students signing up, or aspiring speakers, aspiring CTOs. So if anybody's happy to help out on that, I'll put a link up afterwards. Please sign up. We've made, I think, over 2,500 introductions now, and we've got 1,700 members. So if you're open to getting involved, please do. It's all powered by revenue from recruitment though, so we don't make any money from anything other than getting people jobs. So if there's anyone out there that is hiring or working for a company that's hiring or anything like that, able to put in a good word, please bear us in mind. Anyway, on to tonight. So on to this afternoon. We're lucky to be joined by Kevin Wittek. So for those of you that don't know Kevin, he's now doing his PhD at RWTH Aachen on the topic of verification of smart contracts. And he's leading the blockchain research lab at the Institute of Internet Security in Gelsenkirchen. Sorry if I've got the pronunciation wrong there.
Perfectly fine.
Yeah. At the Westphalian University of Applied Sciences. So, and he's going to be speaking today on interacting with Ethereum blockchains with Groovy and web3j. So Kevin, over to you.
All right, cool. Yes, Barry, thanks for the introduction. So I'm currently today at the lab of my wife, so therefore I'm just on the laptop and I will only be able to see my presentation when I start. So not that easy for me to go into the interaction with the people. So if, I don't know, you all have mic, you can unmute yourself, I think. So I don't know, maybe you just unmute yourself and ask questions or whatever. We have to try to get into a groove there, or if we can get a co-host, maybe he can like a little bit start to moderate this over the chat. I will try to look into the chat or into the Zoom session in between sometimes. So yeah, first I have to share my screen, of course. All right. So, no, like this is stupid. Now you see all the time also, wait, I will just share the screen as the window. It's probably better. Yeah, let's do like this. Okay. All right, yes. So this is kind of based on a talk I also gave as a lecturer at university about blockchain, but I tried to condense it a little bit, make it a bit more developer focused. And also I was specifically asked to bring in some Groovy content, Apache Groovy, the JVM language, for this user group here, which I like to do. So, but what I'm showing you, of course, is very Java JVM related, but I try to make all the examples in Groovy just for fun and to also showcase some Groovy stuff, because I used to be quite involved in the Groovy community in the last years. Now a bit less because I have more focus in the blockchain world, but still I really love Groovy and I think it's a cool language and fun to show the examples using Groovy. Yeah, so a little bit to myself. Of course, I've already had the introduction that said most of the stuff. So I'm currently doing my PhD and leading the blockchain research lab in Gelsenkirchen Institute for Internet Security. And I'm also Oracle Groundbreaker Ambassador. And I think most people from the Java community might know me from a Test Containers project. So Test Containers is an open source project for interacting with Docker containers from inside your Java test, Java integration test, and I'm one of the maintainers there. And yeah, some blockchain projects I'm now also more involved in. Bloxberg is a scientific blockchain run by a scientific community, academic community, international universities, and so on. They're in the consortium, and Sovereign is a big blockchain network focused on SSI and digital identities, and there I have been voted into the Steward Council, so there I'm also involved nowadays. I like to, before we go into the real examples, I like to bring in some historic context, because I find it cool to spin this story for myself from how we ended up with something like a blockchain. And I can personally see or build a narrative where I would say, actually, blockchain is a continuation from some of the very early concepts of computing, like actually things like time sharing systems, and maybe it culminated into blockchain in a certain way. And here we of course see a famous Ken Thompson and Dennis Ritchie in the 70s, while they were inventing Unix basically. So when I started to look into the history of utility computing, so computing as a utility similar to something like telephone lines or electric utility like the power grid and so on. Actually, if you look into this, you find in the 60s, when they started to develop those time-sharing systems, which later became Unix and so on, at MIT, at Bell Labs, they did this. They had this vision of computing as a resource, as a common good, more or less, as a utility resource, something very similar to a telephone network, electric power grid, and so on. And I find this kind of inspiring, that this was already the inspiration, the motivation they had when they were working on this time-sharing system. So they were thinking back then, all those universities, they will have these big mainframes, but they will actually connect them over some kind of network, and then just people will run their computing on this network, on this distributed network. And I find this is a cool vision, and it started back then already. And then, of course, we have now the internet, the World Wide Web, that came from the ARPANET, and one could say this is a thing of a utility computing component, like we all use as a utility. In a certain way, it's an unmetered resource. And interestingly, before we got the World Wide Web, we had something called Project Xanadu in the 70s, which was a bit more academic in the approach, but is the foundation, the conceptual foundation of hypertext. And in Project Xanadu, you were already having kind of the idea of something like the World Wide Web, but also with a constant versioning. So you would not have something like broken links, because you would just more or less append information, and then you would have versioned information, versioned links, and so on and so on. Project Xanadu was much too abstract, maybe also for its time, so it never became a reality. But a lot of the ideas influenced then the World Wide Web, actually, and how hypertext was developed. And of course, in 2006, we had the beginning of cloud computing with Amazon Web Services. Nowadays, cloud computing is more or less ubiquitous, or what is the word? I think you know what I mean. And 2009, blockchain started with Bitcoin. And you can consider the Bitcoin network a decentralized state machine. And in 2015, we got Ethereum as a kind of further conceptual development of Bitcoin. And the great thing about Ethereum is it's not only a decentralized state machine, it's also a decentralized turing-complete virtual machine. And that's what makes Ethereum so exciting. One thing that always got into play with this whole Bitcoin and blockchain stuff is the concept of trust. And in the original paper from Satoshi Nakamoto, the Bitcoin paper, and Satoshi Nakamoto, of course, is a pseudonym. We don't know who is Satoshi Nakamoto, who is the guy that came up with the Bitcoin idea. But here it already says, we have proposed a system for electronic transaction without relying on trust. So the whole idea of all those blockchain thingies is always, you don't need trust anymore, trust in the human contact. But actually, I think one has to be a little bit careful with this definition, because I would say you still need to rely on trust, because now you actually just move the trust somewhere else. You have to trust the correctness of the code. You have to maybe trust the programmers who wrote the code. As a smart contracts, you have to trust the programmers who write the smart contract. So trust as a human social concept is still very much also in play in all those systems. We don't get trust out of this. But what happened is that because of the blockchain technology, we got a new trust architecture. So before we have something classically like peer-to-peer trust, you trust someone else. You have something like Leviathan trust, where you trust in the order of society, you trust in laws and in society order. And you have intermediary trust, which is very classic also in IT systems, where you trust, for example, your bank. You trust your bank that it would operate the transactions correctly. And with the blockchain networks, you have the new concept of distributed trust, where you trust more or less just in the correctness of the protocol and in some more or less statistical guarantees you get from the distributed nature of such a network, which is interesting, which is cool, and which is a new trust architecture. At least that's what people in the blockchain community would argue for. Yeah, but at the same time, and I love this really old quote by, here again, Ken Thompson. He gave this quote 84 when he got the Turing Award. It's part of a talk he gave, Reflections on Trusting Trust. And he says, to what extent should one trust a statement that a program is free of Trojan horses? Perhaps it is more important to trust the people who wrote the software. So with all those big technologies, we don't get away from trust. We have to trust then the developers, and especially non-technical people have to trust those developers still, because it is possible to build in backdoors. And we say, okay, give me enough eyeballs, all bugs are shallows, but we have seen enough very big bugs also in all those critical open source libraries and so on. So the correctness and no backdoors or whatever is not a given just by using blockchain technologies. Also, if some people want to tell this is not true, you still have those human trust factors in there. Okay, so this I just wanted to give a little bit of a flavor touch now. But now let's look how Bitcoin came up, and then how the whole cryptocurrency started, and then we can come next to Ethereum. So 2008, the paper was published. 2009, Bitcoin started with the Genesis block, with the first block in the blockchain. And here we see the number of Bitcoin transactions per month. It increased, and now it's kind of stabilizing, maybe around 10 million here. But we see quite some adoption, I would say. And this is the value of Bitcoin. Of course, Bitcoin is a little bit special as a blockchain technology in a way that it's mainly a currency, a cryptocurrency, and we have a high fluctuation in Bitcoin for whatever reasons. People speculate a lot with it, so it's not really suitable as a replacement for normal fiat currencies. And we have a lot of cryptocurrencies coming up. Like every day, someone can build you can build so easily a new cryptocurrency on an existing one. Like Ethereum has built-in technology, so to say, built-in functions to just build other tokens on top of it. And here we have just the top 10. And yeah, Bitcoin obviously is the most used one, but Ethereum is also pretty important. But Ethereum has a lot of properties that make it different from Bitcoin. And it's not a currency in of itself. It's more of a utility to pay computing cost in the Ethereum network. But we will dive into this a little bit later. Some of the technical properties that are core of Bitcoin and also core of most blockchain technologies. First of all, it's a decentralized peer-to-peer network. So we have a lot of nodes and they all communicate with each other over different peer-to-peer protocols. Then you have a so-called public distributed ledger. Distributed ledger, basically an append-only commit lock. You can think about it like this. And this is implemented as a blockchain data structure. We will look at this in the following slide. This is just for making this append-only lock ensures the integrity using some cryptographic ideas. And then, and of course, that's also what why blockchain as a technology has a lot of its bad reputation from. You have often this proof of work based consensus, and the one in Bitcoin, and we will actually look how it looks in a simple, funny, groovy implementation. I did the proof of work in Bitcoin is based on a proof of work algorithm called Hashcash, which was invented earlier, and yeah, I will not go into these details, but it uses mostly some statistical properties and probabilities to make this secure. It doesn't secure really correctness by using something which is called Byzantine fault tolerance. Byzantine fault tolerance is a property of distributed systems. You have this in I don't know, aerospace, in rockets or whatever. Like if you have multiple systems, they should be Byzantine fault tolerance, meaning you still get the correct values out of there, even if some system sensors are malfunctioning. And there are a lot of very cool and complex algorithms to ensure these fault tolerances. You don't have this in Bitcoin. Bitcoin is kind of using brute force statistics with the proof of work, and I will explain a little bit after we look into the algorithm. And then, of course, Bitcoin is famous for incentivizing people to invest this power to the proof of work by giving you some part of a transaction as an incentivation, a transaction fee. And you can scale those depending on the load on the network. Yeah, so a blockchain data structure normally looks like this. The general idea of the just structure is the above one. So you have just a hash and then a follow-up hash that takes the former calculated hash of the former block to make up its new hash, and thereby, if you want to manipulate something by putting another data into the middle, you would need to recalculate all those hashes that follow afterwards. Which is not in itself super expensive. You could just recalculate all those hashes, but this is where the second image comes in place, which shows more or less the data structure of Bitcoin. And there you have to add this one field, the nonce, which is a solution to kind of a cryptographic puzzle, so to say, and this makes it more expensive. This we will see in the code in a bit. Yes, after I explain this algorithm, how a proof of work works. So this is also funny. The algorithm for proof of work that Bitcoin uses is based on an algorithm called Hashcash from Adam Back. He invented this already in 1997. And this was proposed as a system to counter the abuse of unmetered internet resources. For example, email is a more or less unmetered internet resources. That's why we have email spam, because it's basically free to send out email spam. And he proposed that an additional computation should be added to before sending an email to calculate a valid header for an email. And this is for sending a single email. It would not be expensive for a user, but if a spammer would send thousands of emails, it would get expensive. That's where Hashcash comes from. And the idea is to just have this header that contains some parts of the message, basically. And then you have one field in there which you can guess or which you can change yourself. And then you have to now find a hash for this header that starts, for example, with 5 leading zeros, which is kind of random, the answer to find this. So you just have to try out a lot of values until you find this. And yeah, this is exactly from the concept the same how Bitcoin does this. And let's just look for fun in how this would look if we implement such a blockchain that uses proof of work in Groovy. Okay, I will move into presentation mode. Oops. Oh, I have to, of course, then share the other screen. Are there any questions so far, maybe? Okay. So, yeah. maybe before we look into the implementation, let's look in an example code how to interact with this. So it's just Java objects here. It's kind of, yeah, I just made a Java implementation of such a blockchain or Groovy, basically the same. And we create a new blockchain here. I call it Groovy chain. This is the genesis data, so the data that is stored in the first block. And then we specify here a difficulty, and the difficulty is for the proof of work, how many leading zeros I have to have. So here this means 3 leading zeros basically. Yeah, and then since in Groovy we have operator overloading, I can show you in the code how it looks. Instead of having some method, we can use an operator to append stuff to the chain. So which I'm using here, this left shift is cool, I think. So we add bar, we then add buts, and then okay. So we had this three blocks then in the chain. So each block contains 1 data field. Let's run this. It should not take super long. Okay, don't know, maybe it was compiling something first. Okay, so now we see kind of how the chain changes after adding things. So yeah, basically we are adding those. First we have foo, then we added bar, and then here we also added buts, and then there is a lot of other stuff in here. This is the hash of the previous block, and this is a nonce. This nonce I had to guess. Sorry, I had to drink a little. So let's check the implementation. Let's see here. All right, so yes, I don't know how many of you know Groovy. I just assume you don't know Groovy or you don't know a lot, so I will just say also some fun facts about Groovy. So first of all, you don't need semicolons, why I put one here, useless. You can add to string annotation to Groovy classes, and you get automatically a nice to-string method generated from Groovy. So we now have the Groovy chain. We define it as as a class that contains a difficulty and has a number of blocks. And when we add a block, we add it and mine it directly. This means creating a new block that contains this new data, contains the hash of my previous block, and then I'm in this block, I'm mining the block itself, and then I'm adding it to my list of blocks. And the operator overloading, by the way, just works by overriding the left shift method. So in Groovy, if you override certain methods, mostly something like plus, left side, so depending on the operator, it automatically you have the operator overload. And now we have the block class. The block contains the data, the previous hash, and the nonce. So it looks basically like this diagram of Bitcoin I showed. And now the mining is very, very simple, but it's at the core how the Bitcoin proof of work also works. We calculate the hash and we check if it starts with difficulty, so starts basically with those leading zeros. And if not, we just increase the nonce by 1. So we just add this, and by the cryptographic properties of the SHA-256 hash we are using, it doesn't really matter how we change the nonce, so increasing a counter is totally fine. And yeah, then that's how it works. And therefore here we see for this block we had to increase it 11,000 times, the nonce. So run 11,000 times through this iteration. For this other block here, 2,000 times. And now what I also did, just to do some fun stuff with Groovy, I wrote a small benchmark, which is not a perfect benchmark, but it's just a fun thing to do. So in Groovy, we have something called the benchmark interceptor already built in. And you can get it by using a so-called proxy class, proxy meta class from from the class you want, and then it can basically attach a method interceptor. And then every time a method gets entered and exit, it records a timestamp. So thereby you can build a easy benchmark. It's not a real good benchmark. You would use GMH for something like this, but for something small, it's easy and fun to use. And here we just run a benchmark that says, okay, basically mine n blocks, I blocks for this difficulty. Okay, and then we get some statistics out here, and then we make some calculations. I'm using the follower library from Apache Commons Math here, but this is now called different. This was org Hipparchus, yes, Hipparchus library. You can make some easy mathematical statistics. So we just try to find a distribution about how each call to this mine method, how long it took, roughly. And yeah, so now let's just run some benchmarks here. First with difficulty, so basically increasing the difficulty by 1 digit all the time. Is it running? Yeah, it's, wait, I will maybe increase. Sorry, I had the laptop in battery saving mode. That's why everything was maybe a little bit slow, so I will start again. Yeah. Okay, still running, by the way. So yeah, just we see some things. This first of all, this descriptive statistic is pretty cool. Is like you just put a number of values in there, and then you can get the statistics out, and they already give you things like min, max, mean, standard deviation, like kind of the things you would use in those Python data science libraries and so on. So I think this is nice. It's nothing to do with Groovy, it's a Java library, but yeah, I think it's cool for those easy use cases. Why not? So the first time when we run it, we had a mean. Let's just look at the mean. There, it took around 3 milliseconds to mine a block. Next, difficulty already 8. Then now we're at 3 digits. It's 23. 4 digits, 125 milliseconds, and then 1,388 milliseconds. So it's, I don't know what we could plot this now, and it's exponential or higher, whatever. But there you see how with the difficulty you can really change the speed a lot and influence how much power you have to invest. All right, so this was a small initial excursus. Maybe it has nothing to do with Ethereum itself, but showed some cool things what you can do with Groovy in general, also this benchmark stuff. And I think it's good for people to get a feeling how this weird proof of work stuff always works. And it's really simple and kind of stupid. So you're really burning CPU cycles with something quite stupid there. But it's also super simple to understand. And now, how does this work? How does this ensure the safety? So the idea is that all those people in the network are always participating in this proof of work. So trying to find the next block, the norms for the next block to mine this. And then the chain becomes longer and longer and longer. And everyone always uses the longest chain because the longest chain is the chain that has the most work invested in it so far. Now, one attack is called double spending attack normally. So they try to spend the same Bitcoin multiple times, 2 times, for example. So you say, okay, I send in the transaction, it gets mined. Now I try to send the Bitcoin again, the same Bitcoin, and basically roll back locally my blockchain and remine those blocks. And now I try to be faster than the other people mining this chain, getting more blocks in there so that my new chain overtakes it, and then I could spend my money 2 times. And this, for this attack, it's a double spending attack. But for this to be successful in the case of Bitcoin, you basically need statistically 51% of the hash power of the network. And yeah, in general, Bitcoin makes the assumption if you have so much power to make malicious attacks, it's more useful to use them for good mining to support the network, and then you get also the money from the mining, the incentivization. So Bitcoin security is based on those statistic probabilities that it's very hard to catch up the mining of the longest chain if you are a malicious attacker and you don't have more hash power than the network, and that in general people are incentivized to work honestly with the network because they would actually get more money from this. Yes. So, someone asked, what about if a state actor or some malicious entity wants to? Yeah, maybe just phrase your question personally if you can unmute yourself. Give a bit more detail.
So, what can you hear me?
Yeah, perfect.
So this assumes you care about the money, but how much money would it be? Because the state made, for example, say 2 states go into war, so Russia and America or China and America, and they want to attack, so they want to disrupt the Bitcoin. How much would it cost them to do that? So they decide they're willing to pay to cause damage.
So I don't have numbers, but I think you can find numbers because you always find that the energy consumption of the whole Bitcoin network is like more than the Netherlands or Belgium, or like quite a high amount already. So you would invest considerable amount of energy and also hardware. You need to have the hardware available, and you need to get then more hardware into the network without the good actors noticing it and countering it by maybe also raising it. So I can't give you numbers. It's theoretically, it is possible. We also have seen double spend attacks in the past, or 51% attacks, especially if you at the same time start attacking network infrastructure and network topology. Because if you can do splits in the network, then you have potentially other outcomes. So, for example, US makes sure that kind of the US part of the network is isolated by cutting all the connections to China. Then at this point, we would have a fork of 2 networks running. One runs in US, one runs in China. If there is no connection between them, no physical connections on the network, and then once they would come up again, they would think, and basically the longest chain would take over. And I think in those scenarios are possible to disrupt it if you are also able to control the internet infrastructure in a certain way. Yeah.
And then a second question, also on the same topic, the mining conglomerates, the mining pools. If someone in charge of these mining pools, I think it's only 2 or 3 or 4, they got together, they would have 51%.
Yeah, that's
is that a danger?
Super big danger. Yes. Yes. So yep. in this case, I think also I don't know, the decentralization of Bitcoin has failed in this way. So I'm not super invested in the dynamics of Bitcoin, so I'm not sure if they try to counter this in a certain way. But yes, this is a real danger. I agree. All right. So yeah, so a little bit more about blockchain in general before we dive into Ethereum. So these are some people of the hardcore blockchain community. They say these are the 5 pillars of an open blockchain. They used to say these are the 5 pillars of blockchains. Only if these properties hold true, then you have a blockchain. I would say only then you have an open blockchain. And open means everyone can participate. Borderless means there are no borders in the like nation-based borders or limitations. Neutral, censorship resistant, very important. And being public, also being publicly readable. But nowadays we have many systems we call blockchains that don't comply to all of those properties, and therefore people would say, and I would agree with this, nowadays we have different types of blockchains. And those open blockchains, yes, they should have these properties. And these examples are the public networks, things like Bitcoin network or Ethereum network. But then we have the other side of the spectrum, are the private closed networks, where they are just running inside some companies, where the companies together operate a blockchain together. And here we have things like Hyperledger Fabric is normally a technology here, or R3 Corda, which is just used basically by European banks, I know, maybe also US banks, not sure, for interbank communication, basically. Yeah. And you can also use a technology such as Ethereum and build your own blockchain network that falls somewhere in this quadrants. So you can have, for example, a public closed Ethereum blockchain. For example, Blocksberg, the scientific one, is such a network because it is doesn't use proof of work, it uses proof of authority, and also only authorized nodes are allowed to mine new blocks, and authorized nodes are just universities that have been certified as a university or identified as a university. And then it becomes quite cheap to operate such a network, comparably cheap to other distributed systems, I would say. Okay, so now when we go into Ethereum, we are directly landing in the domain of smart contracts, because I think this is what makes Ethereum cool, what makes Ethereum in a certain way. And this is very nice, a quote that is often used in the blockchain smart contract world, where they say, okay, code is law. With smart contracts, we make code law, or code becomes a law. And it has been quoted from Lawrence Lessig, and what I like most of those quotes, that the quote is wrong. So he said this, but he said this in a completely different context. He said this, that we have to be careful that technology doesn't rush forward. The big internet companies don't rush forward, and then technology dictates the laws to us. That's what he means. So he doesn't say we should encode our laws in code. He says a different thing altogether. So I just like to point out this fallacy many people in the blockchain community have. Yes, so the law of cyberspace will be how cyberspace coded, but we will have lost our role in setting this law. This is the danger we have. And this is also the danger we have with blockchain systems in general, I would say. And then smart contracts itself has been first mentioned in a paper by Nick Szabo in 1997. This was called an article, Formalizing and Securing Relationships on Public Networks. And then he wrote an article derived from this. It's called The Idea of a Smart Contract. And here he thinks about a smart contract as some code that automatically processes or executes a business transaction, potentially a business transaction involving money. And in this case, he gives an example, a vending machine basically has a smart contract included. You put the money inside, then you get the product. It's a kind of an automated process. And actually it is, I don't know by if the definition is so true, but in certain definition, it is an automated business transaction, or this business contract gets executed, however you would define it. But of course, back then, you already had a lot of those vision that would involve those cryptographic key components, like public, private key cryptography, and basically thinking about the model that a car would only start if a lease had been paid, for example. And yeah, based on this broad concept of smart contract, we more or less got smart contracts in Ethereum, and Ethereum now the second largest cryptocurrency platform or blockchain, public blockchain network next to Bitcoin. And it was first described in a white paper, in a conceptual white paper in 2013 by Vitalik Butekin. And then in 2014, Gavin Wood conceptualized the Ethereum virtual machine in the yellow paper. And I just looked up, like, what did Gavin Wood do before? Before he did his PhD on music visualization, which is cool. Maybe it's cooler than Ethereum development. I like this. It is very detached from the other side. Yeah. So he wrote this Ethereum virtual machine because in Ethereum you have a Ethereum bytecode. A smart contract gets compiled into Ethereum bytecode, and this bytecode then gets executed in an Ethereum virtual machine. A little bit maybe to how Java does it, with Java bytecode being executed from the Java virtual machine. Now the Ethereum virtual machine then can be implemented in many different languages. There are, for example, Java implementations of the Ethereum virtual machine. So then the Ethereum virtual machine is implemented in Java, running on the Java virtual machine itself. Hyperledger Besu is such an Ethereum client. The Ethereum language is basically turing-complete. Basically Turing-complete because it has kind of a protection against infinite loops built in. So in this way, it is just quasi-Turing-complete, one would say. And it is defined as it allows a rich statefulness. Rich statefulness means it's not only stateful, you also have the history of the state of the smart contract encoded in there. And if you are developing something with a smart contract, this is called a DApp normally, decentralized application, where parts of your application run, for example, on your phone, and other parts don't run on the server, but instead run in the Ethereum network. Many different networks, they are all Ethereum networks, but the most famous one is the mainnet. This is what people, if they say Ethereum, they mean normally the mainnet. But then there are test networks like Robson. There is Ethereum Classic, which is kind of a fork of the old mainnet. These are all proof of work networks. But then we also have proof of authority networks, such as Bloxburg, which uses a completely different consensus algorithm. And people can just also run their own private networks in some clouds or whatever. This is perfectly possible. Just you have then Ethereum as a runtime platform, maybe. Yes, this is an example how a smart contract looks. It's very similar to object-oriented programming, I would say. So a smart contract is like a class, basically, that you can instantiate. So here we don't see a constructor, but it can have a constructor. It can have fields. They are mostly fields of this instantiated smart contract then. So like instance field in a Java object. And then you can have functions, public functions, private functions. And these can be functions that either change a state of a smart contract, like this store one, this just stores a number, or it can be just views that just give you back a value. And the important thing about those that change state or that have to execute code and just don't give you back a value is they need to be paid to be executed. They need something called gas. So when you execute a smart contract, you're providing a certain amount of Ether. Ether is a currency on Ethereum, and say, okay, you can use this Ether to pay the execution of the code, so to say. And this Ether might run out. And this is a safeguard against infinite loops, so that you can't block the network, basically, because then the gas will run out. And the gas price and gas cost has its own dynamics, so it can rise if there is a lot of load in the network. Therefore, it incentivizes more people to participate and so on. Quite interesting as well. Okay, this we will skip. What we will look at now is how we can interact with Ethereum from inside the JVM. We use Groovy now again as an example, but we could also use Java or Kotlin or whatever JVM languages. And we're using web3j, which is an open source library for interacting with Ethereum. Web3 is kind of the, so to say, protocol you would use to interact with Ethereum. So Web3 library is a JavaScript reference implementation. Then we also have Web3 Python or whatever. Web3j is the Java variant. And here we see the rough overview of our architecture. So we have a Java application, and it communicates with an Ethereum client using JSON RPC. You can use this over different connections, HTTP, WebSocket, or even IPC. And yeah, an Ethereum client is an Ethereum node. So those different nodes making up the Ethereum network, they are called Ethereum clients. So that's how it looks, and it feels a little bit like client-server communication, and we will see this now in an example. Here's a bit more detailed how it actually works, the internal workings of web3j, but I think we can skip this. Now let's check some code. So first of all, what I want to show is how you can get a smart contract. No, let's start different. Let's start by checking how you can just read stuff, how you can just read transactions that are on the ledger. This is fetch transactions here. Oh, sorry, I'm not sharing the correct screen. All right, okay, IntelliJ. So this is now Groovy code again. It's a Groovy script. So with Groovy scripts, you can just have like top level code without having any class or whatever. A little bit like Python scripts or Bash scripts is quite cool for this small things to do. So we have here a URL we want to connect to, a WebSocket connection actually. This Bloxburg is a public Ethereum network that is more or less free to use. As I said, is run by academic institutions, universities. So we are creating a WebSocket connection to this. We connect to it. And then we create a web3j client, so to say, by building it based on this WebSocket. And now what I want to do here, and I just use some Groovy constructs to make it a little bit more fun and more groovy maybe. I'm using here this web3j, this with, this Groovy with leads, makes it possible that now every method I call in this closure, I have here, this is a closure, Groovy closure, would be called on the web3j object. So I get a lot of methods I can call here directly without saying web3j dot, just for fun, not that it's necessary. And then this is a way to loop in Groovy. There are so many different ways to loop in Groovy. I found this fitting for this example, what I want to do. So what I want to do is I want to get all the blocks between block number 5 million and 5,100,000. I want to load them, and I want to see how many transactions have been in this block. So you can say, okay, for each of those numbers, again, you specify a closure here, a Groovy closure. It's like the lambdas in Java. And so what I do, I call this web3j method, eth get block transaction count by number. Okay, this creates an check here. This creates where's the return value? Yeah, it creates a response object basically. But does it? Yeah, but we also have to send it. So if you use the synchronous API, we have to send it to have a blocking call, and then we get the. So then we basically get the result from the send. There are also other APIs. There is an asynchronous one where you can specify a listener, or there is a reactive one, but the reactive one has some bugs, so it has some blocking calls, therefore it's not very fast, which is a shame. But here we just call it like we would call an HTTP service maybe, and we make it blocking, therefore the send, and then we can get the transaction count. I could get other things here. I should get. Okay, so I could get the raw responses. I could. So since I already do the transaction count here, transaction count by number, I don't get the interesting stuff, but let's assume I would do eth get block by number. So I could also do something like this, get block by number, then I get all the information that is in the block. Okay, and now I just use again this descriptive statistics object to get this distribution summary basically of the values. So let's execute this and see. Okay, now it takes some time because for each block it makes a new web request basically, but at least using the same WebSocket connection. So we pulled out 101 blocks because it's including interval here, and the mean of the number of transactions in this block was 2, minimum 0. So we have also empty blocks in Bloxburg. This is because it's a proof of authority blockchain, and the proof of authority one is kind of with a constant rhythm generating new blocks. If there is a maximum, there were 70. Yeah, but just what I wanted to show you, like getting data out of the blockchain is like having kind of a web call, like just an HTTP request or something. Now let's go to the smart contract stuff. What I have here now in the resources, I have a smart contract file. Solidity is the one we saw here. Is a smart contract. Now what I can do when I open the Maven, so there is maybe I often open the POM. Okay, so I use Maven here for building, but you can of course also use Gradle. I'm using this web3j library for the interaction, and there's also a web3j plugin. And this web3j plugin gives you this task, generate sources. And if I run this, it takes some time. Okay, and then we see something, generate sources. Blah, blah, blah. Okay, success. And what I now have, I have this directory org web3j model, and now I get a Java object here, Java storage object. And this is the Java representation of this smart contract, or more specifically, it's actually not a representation, it's a client, an API, a Java API to interact with this contract. So I automatically get some constructors, and I get the methods that are kind of the representations of the smart contract. But then if I would call them, I would actually do remote calls into the blockchain. And now we check how we can interact with this smart contract example. So now what I'm having here, maybe I just switch to this quickly. I have this thing running here locally now. This is called Ganache. It's a tool, open source tool to run a local Ethereum blockchain. You could also use something with Docker, or you could use a remote one, whatever, use test containers. But it's kind of convenient, and you have this UI, you see a little bit what is happening in the blockchain. That's why I like it. So I have this running. You don't have to install it, you can directly run it. And now let's go back here, let's go to the code. Here it's running locally, therefore we will connect to my local host here. I will connect using HTTP this time, not WebSocket. And now, yeah, here is my private key. You should not remember this, or it's even in the recording. Oh no. So it's okay because it's just a private key from this dummy account of this local Ganache test network. So here we create a credentials object, which is then basically enclosing the private key. But web3j also has more APIs for creating real wallets in a file somewhere encrypted and so on to make storing it more safe. And now I want to deploy the smart contract. Deploying it means writing the code onto the Ethereum blockchain. So therefore I just can call deploy, I give it the web3j client, my credentials, and here I have to specify gas cost, gas price, and gas limit. Okay, this is just then for paying this deployment basically, and also for in the future paying the interactions I have from my Java code. Yes, and then I can start interacting with it like just from Java, or in this case from Groovy, like I would do with any other object basically. So here I check, okay, which value is initially in the smart contract. Here I'm storing a certain value. I check which value I have then. Here I'm storing another value. I'm printing it, but actually we will not see a big surprise about what will happen here. Yes, so we see exactly then those values we stored are then on the blockchain. Yes, especially since we do synchronous calls here, so we are sure this transaction has been executed before we run the next call. Else, if we would not do it synchronously, of course, we would need to check. There could be certain race conditions happening there. Yes, and if we look back at the ganache, we will also see now that so here I made some other stuff before the call, but here this is a contract I deployed now from the Java code, and these are the contract calls. And if we check here, different stuff, these are the numbers we saw from before: gas limit, gas price, transaction data. This is actually the bytecode of the Ethereum bytecode of the smart contract we deployed. This is transaction data. And yeah, these are now the other calls. Here we see the transaction data is much smaller. This is a storing. So we just see the storing. The retrieving we don't see, because the retrieving doesn't create a transaction. It's just a view. It doesn't change the state of the ledger. Yes. So yeah, as you can see, basically interacting with Ethereum is from inside the code. There is no magic. Like web3j makes it quite easy, quite comfortable in my opinion. Very similar to interactions with other systems over the network, I would say. So this is now something I wasn't aware of. This Connor Svensson, he is one of the maintainers, or I think even the lead of web3j. He saw when when this talk here has been announced, he said like, oh, by the way, do you know there's web3j unit? We even use test containers there. I didn't know before. I didn't try it out yet, but I looked at it. It looks pretty cool. Web3j unit is a way to, in your test, basically have a Ethereum network automatically spun up via Docker container. Then you can deploy the smart contract in there and basically do your integration test. I think the idea is really great. I was always thinking like, oh, I should at one time build such a thing. Obviously, it already exists. They built this, but it's a good idea, so it just makes sense. All right, and yes, here we see how it looks. This is some Kotlin code because they wrote it in Kotlin. So I just copied it from their documentation. So they have this annotation EVM test, and this spins up automatically an Ethereum network, single node network, either inside the JVM directly or using Docker and test containers in a container. And then you can interact with it and make a thread. I think it's super cool. There are other tools for testing smart contracts like Truffle and so on, where you try it more with the languages you have for writing smart contracts like Solidity and so on. But I would say this is really inferior to just doing it with Java, because in Java we have so mature tooling to do those kind of things, to do real nice integration tests. I think is a real great approach, and I will try this out more in the future. All right, okay, yes, and like some words about Oracle, they were all groundbreaker. But this also holds true for most clouds, and I think it's kind of a little bit interesting. So many clouds offer blockchain integration or blockchain services or whatever, but most of the time these are then Hyperledger Fabric based. So most of the time it's this. So it's already for kind of a private network or whatever, some private infrastructure, intranet use case. And yeah, so Oracle one is based on Fabric. Azure one is also based on Fabric, I think. And then people could argue, okay, this kind of setup, if it's just in this one cloud running in this one account, is this even a blockchain? I would say maybe not. But at least they support, the IBM ones don't support this, I think. But at least the Oracle one support a hybrid network where you connect with other nodes that run in other clouds or in other networks or on-premise. And I think this is super important. A blockchain network that just runs in the same cloud provider, that makes no sense. So it's not decentralized, it's not even really distributed anymore. So then you don't need a blockchain, in my opinion. But sometimes if you maybe have this blockchain need without needing a real blockchain, something like this, Oracle blockchain tables is even all you need. This is kind of cute. It's just having your normal relational database, and you just have there an append-only mode in the table. So this is definitely not a blockchain by most definitions, but for some of the use cases, maybe all you need, ensuring append-only integrity on your data. Okay, yes, I tried to make it more or less on time. Very happy. I'm very open for any more discussions and questions or whatever. Feel free. We recently started with GitHub Sponsors program with test containers. So if you like test containers very much, or your company is using test containers very much, you can sponsor it here over GitHub Sponsors, or sponsor me personally if you want. But if you like test containers, it's better to sponsor test containers directly. And yeah, thank you very much. I hope you liked it. And as I said, I'm happy to have a discussion with you now.
Thanks, Kevin. It was excellent, and great to see some Groovy code as well. I haven't seen that for a while. But, yeah, that was fascinating. Thanks very much for the talk. Ian, I don't know if you want to curate the Q&A. Do we have some time for a couple of questions, perhaps?
From my side, I'm fine, yes. If there are questions.
Well, are there any questions?
Oh, let's throw it open. Anyone, don't be shy.
Yeah, I have a question. Can you guys hear me?
Yeah, sure.
Yeah, we've got you.
It's kind of deviate from the more technical aspect of this presentation, and great presentation, by the way. Just wanted to ask if you can have like an estimate, or can somebody estimate when blockchain as a technology will be used for like mainstream, the way we use banks, for example. Because now, even though, it's used in some enterprise scenarios, it's really hard for somebody who's not technical to get down and follow everything that's going on, and to create an account and to start doing transaction and basically start using it on an everyday basis.
Mm-hmm.
So that's, I guess, my question. Thank you.
So from my point of view, as a replacement to fiat currency, I'm not sure. Maybe also only if it's kind of controlled by European Banking Union or whatever, something like this, and then it would maybe just look like using in your normal online banking. I could imagine that they would start using some blockchain-like technology to just better automate their interoperability, because that's what blockchain is very good at, in a kind of easy onboarding, easy technical onboarding and interoperability, because the protocols are pretty fixed and encoded in the system. And then I think actually with most blockchain related use cases, I think as soon as we would have a more or less productive use case for broader adoption, it will be a transparent technology, so to say. So it is really kind of a network infrastructure, internet infrastructure kind of technology, kind of like a protocol. Like most people are not really aware how HTTP works, probably not aware how TCP/IP works in the technical, in our workings. And but we can all use the internet perfectly fine. My grandmother maybe not, but my parents can use the internet. And I think this might be that we have applications, decentralized applications, that make it such transparently possible to use blockchain for certain use cases. And from the feeling and from my involvement in different projects, what I think are the two domains where public blockchains might become widely adopted in the public is identity and in a certain way certification and verification. So which is kind of combined. Yeah, it's a little bit abstract, but it's basically proving certain claims about your identity. So this whole domain is called self-sovereign identity, but it's things like diplomas, driving licenses, those kind of things. I see a lot of movement, even from the governments, even from things like European Union, and they really try to solve this, even on a European level. but you can probably imagine how bureaucratic such projects by the European Union are.
Yeah.
And yeah, therefore it's hard to say when this really become adopted. So one could say in Estonia, it is actually adopted, but in Estonia, so they have the electronic ID card or electronically enabled ID card for a long time, and they have a lot of services by the government and so on completely digitalized. And they always say, oh, we do it also with the help of blockchain, but people don't see any blockchain stuff in there. And actually the blockchain is kind of like a proto-blockchain, like it is this database, it's a pen-only database, but not this peer-to-peer network. So yeah, but in this case also people don't see it, it just looks like a normal web service. So
okay.
Yeah.
Oh, thank you.
Anyone else? Kevin, I've got one question for you, if you don't mind, unless anyone else wants to jump in. One very interesting use case I've seen for blockchain technology is in energy, right? In green energy, where people are kind of generating their own electricity and then pushing them back into the grid. I know that I think there was an experiment in Brooklyn. It was called, Brooklyn microgrid. If anyone's interested, in check that out. That's a very good use case, practical use case for this kind of technology. I don't know if you've got. Are there any other ones that we should maybe keep our eye on? That apart from self-sovereign identity and green energy, and anything else perhaps in the news, maybe with newspapers, anything like that?
Yes, so microgrid definitely is true. I also involved with some German research organizations, also from the energy sector, who try to invest. It's very complicated, but it's a great use case. Two others where I'm personally involved in and I like very much is the one they're a bit related. The one is in the science domain. It is about integrity of the scientific process, which is closely related to reproducibility of science. So actually I'm with my wife together in a research project involved with this, where we also try to apply it to a scientific machine learning pipeline, so to say. So I hope this will come and this will help there. And the other one is in copyright and media licensing. And
very good. Okay, yeah. Like for musicians and stuff like that, right?
Yeah, exactly. And I'm involved with a project, and they are called ISCC codes. It's like content codes. It's also an open standard, and they try to become an ISO standard. And these are hashes, file hashes that are content aware. So pretty cool technology. So which means the hash has so if you have an image and then you have the same image that just has one pixel changed, then with a cryptographic hash, the hash would be completely different. But this content aware hashes, they have a very close distance then with each other. Then of course you have something to better follow those copyright problems. So this makes a lot of sense, and publishing those kind of hashes in public registries in a certain way with entities that can certify that that people have published this or something like this, maybe.
Okay, so that'll be the end of the Led Zeppelin Stairway to Heaven kind of debate. You need to go to court.
Exactly. But
Fantastic.
these codes, they are in general, they are not directly related to blockchain. These ISCC codes, they are cool technology, but there are maybe other use cases as well. And for many blockchain use cases, they make a lot of sense, because with the cryptographic hashes, it becomes a bit too opaque.
Yeah, brilliant. Well, Kevin, I mean, that was fascinating talk. Really, thank you so much. I'm sure our audience absolutely loved it. And yeah, I think unless anyone else has anything else, we maybe just close the session. Ian, anything from your side?
No, I enjoyed it very much. Maybe in the future, at one point, I can visit in person for a follow-up one. And yeah, I wish everyone a nice weekend, and thank you for having me.